Hello! Today, I describe Lagrange points and halo orbits around them. The Sun-Earth two-body system has 5 Lagrange points where the gravitational fields and inertial effects cancel. I show these in the Wikipedia image on my left. This image also shows the Moon's orbit near Earth. If a spacecraft is perfectly placed at any of these points, it will, theoretically, stay there without thrusting to maintain the position relative to the Sun and Earth. However, only 2 of these points are stable, meaning that any error in placement of the spacecraft will not cause the spacecraft to wander away. Only L4 and L5 are stable. Space garbage may collect at L4 and L5 since they are stable points. Therefore, you may not want to place spacecraft exactly at these locations. Luckily, you don't need to do this because you can use halo orbits to travel around these points. Halo orbits can be used around any Lagrange point, including those that are unstable. However, all halo orbits require occasional small rocket burns to maintain the orbit. The James Webb Telescope is currently in a halo orbit around the Sun-Earth L2 Lagrange point. The Earth-Moon two-body system also has 5 Lagrange points that correspond to those of the Sun-Earth two-body system, as I now show in the image. However, it's more difficult to maintain halo orbits around these points due to the Sun's gravity. The Sun's gravity causes these Lagrange points to shift as the Moon moves around Earth. Therefore, it's difficult to model this as a two-body system. It is more accurate to model it as a three-body system. It is possible to place a spacecraft at Earth-Moon L2 in a halo orbit like the James Webb Telescope's halo orbit. However, it may require a significant amount of fuel to maintain it. If you place a spacecraft at the Earth-Moon L2 point and do nothing to maintain the position, the spacecraft will eventually do one of 3 things: fall into an Earth orbit, be ejected into deep space using an unintentional gravity assist from the Moon, or crash on the Moon. The first seems to be more likely based on our simulations. A halo orbit around L2 can involve movement around the Moon and L1, resulting in a very complex orbit track that is more accurately described as a cislunar trajectory. I show a 99-day simulation for this type of trajectory in the following 2 images, where the spacecraft's orbit track is shown in red and the Moon's orbit track is shown in yellow. Earth is near the center of both images. This spacecraft trajectory passes near L1, the Moon, and L2. It also requires periodic thrust to keep it from falling into an Earth orbit, drifting away, or crashing into the Moon. I now show a video of the simulation. Here you see the Moon in the center and the spacecraft represented as a red sphere. The camera is located at L4, but always looking at the Moon. Note that the spacecraft is wandering around the Moon, L1 and L2 as the Moon moves around Earth. Thank you for watching this video. If you find it useful, please give it a like and consider subscribing to the channel. If you want to be notified when new content is added, click on the notification bell. We also need your feedback, so please leave comments. Goodbye.